Hi, I'm Lee Tushler with EE World and Design World, and I'm here with Dan Carnovale from Eaton. And Dan is going to tell us a little bit about the difference between an ordinary circuit breaker and one that detects arc faults. Dan, you got a cool little demo here. Why don't you tell our readers where we are right now and what you're going to show us?
Okay, well, thanks Lee. We're at the Eaton Power Systems Experience Center here in Pittsburgh. And in this Experience Center we can show firsthand demonstrations and show people through visual learning how things work. So this demonstration is basically how an arc fault circuit interrupter works. In this case it's called a dual purpose arc fault circuit interrupter. It works on series and parallel arcs and ground faults as well. So I'm going to show you what happens when you have a normal circuit breaker. This is a normal circuit breaker that we call a thermomagnetic breaker, and basically works on the properties of bimetallic strip. If a bimetallic strip sees too much current, the metals separate because they heat at different rates. So when that happens, a normal breaker would trip if you have a fault. But in this case, we're creating something called an arcing fault. And as you can see, that normal breaker can't trip on that kind of a fault. The reason is because that current is limited by that arc, the resistance of the arc. So now what we're going to do is we're going to change this over to the arc fault circuit interrupter, and we'll do a similar kind of fault, and we'll see this, and we'll do a similar kind of fault and it'll trip. And what has to happen is it has to sustain the arc just enough to determine what's going on. So if you hold up that breaker, I'll show this breaker and you show that breaker. The difference between these breakers is that this is a thermomagnetic breaker, that's a thermomagnetic breaker, but what you see in the bottom is actually a circuit board, a printed circuit board, and a lot of electronic components, including current transformers and some MOVs for surge protection. What this breaker detects, again, is just high currents. If I have 10,000 amps, it's going to trip like instantly. If it has an overload, if you have your microwave and your hair dryer and everything plugged in and too much, it'll trip over several hundred seconds, for example. But what happens with an arc, again, is it defers a little bit of the current. It actually takes away from the current because of that resistance. And so what happens is the thermomagnetic part of this might take a few hundred seconds to trip, more like an overload condition, but as you can see, it's a dangerous arc condition. So what we want to do is we want to detect that. What the circuit board in there looks at is not actually magnitude of current, but it looks at the frequency of the current. And an arc has all frequencies, and so the broadband spectrum of the frequencies, we pick out one particular frequency, somewhere around 1 megahertz, and we determine if that occurs, that's not a normal arc, and we want to trip.
Okay, so just to be clear about a couple of things here, in a normal circuit breaker, it detects the heat generated from an overcurrent, but not heat from an arc, which isn't at the breaker. That's the problem, right?
That's right. So the heat in the circuit is really how much current you're drawing, and through this thermomagnetic property, again, if I have this breaker on, it will trip in that position if I get, let's say, 1,000 amps, 10,000. If you accidentally connected the wires together from the black and white wire way out, let's say you're installing a ceiling fan, you install those together, then the breaker would see that as a very high current and it would trip, and that's normal. Or if you have too many loads, that's normal. But in this case, the arc that's occurring is out there, not back at the breaker, and so that heat that's generated could potentially cause a fire. And so that heat, you're exactly right, is what we're trying to prevent out there. We don't see that back at the breaker. We see a much lower current. And by the time that that arc is extinguished, maybe 100 seconds or a couple hundred seconds later, if the breaker trips at all, it's too late.
Gotcha. And there's a couple of interesting components on the arc fault detection circuit. This looks like a current transformer. And are these MOVs?
That's right. So inside that arc fault circuit interrupter, what happens is you're also, in this particular case, it's a dual purpose one, so you're looking for a thing called a ground fault. And what happens if you've seen ground fault circuit interrupters in your bathroom, what happens is the current going in, the black wire, better equal the current going back out. So what they do is they put a current transformer around both of those. And the way a current transformer is if you put that around both, they'll negate each other, they'll negate the current. And if more than 5 milliamps goes through that current transformer, then it'll trip the breaker, because it knows that there's some current going somewhere else, typically through ground, maybe through a person, and at 5 milliamps it'll trip. So we know that not a lot of milliamps can hurt us, so we know that that's what needs to be done. The MOVs in there are for a special case, because actually we have a circuit board in there, but we need to protect against all the surges and things that go on within our homes to protect the circuit board so that it knows when to trip and when not to trip. There's also other features and things that can happen with a breaker like this because it can detect up to 7 different types of faults. So these things are pretty smart nowadays. It'll look for a thing called an open neutral condition. And an open neutral condition is where, let's say the utility feeds you at 240 volts coming in. It's 120 to neutral and 120 to neutral. If somehow that neutral line gets cut from, the tree falls on it coming into your house, what can happen is you'll have maybe 180 volts on one side and 60 volts on the other. That breaker will detect that and trip. It's kind of a little bit of a self-preservation mode because those MOVs would actually get damaged if we had more than about 150 volts on it. But what it's going to do is it's going to trip the breaker, and then it'll actually also protect your loads, all of your electronics.
Interesting. So Dan, are all arc fault detectors also ground fault detectors?
No, that's the difference here, was the dual purpose. So there was a kind of an evolution of arc fault circuit interrupters, and they went from a series arc like you see here with this, where the two lines come together. That would be like if I nicked one wire, cut one wire in half. Another one is a parallel arc where I accidentally cut 2 lines. So there's series and parallel arcs, but then there's also ground faults. So the dual purpose one covers all 3 of those combinations.
Great. Well, that's an interesting piece of technology, Dan, and great advance in safety, I'd say.
It is, and originally they were put into just a few circuits in your house, like bedrooms, where you kind of had to worry in case you were sleeping and things go on behind the wall. But now, even with appliances and things plugged in, it's very important, from a fire safety standpoint to have that kind of technology. And I think early on there was some what we'll call nuisance tripping of certain breakers and things like that. And what happened is, again, part of that evolution is we determined more of what's a normal arc or a good arc, a typical arc, with motors and different types of appliances that might create arcs, and then a bad arc, which of course would be like we saw here that could cause a fire.
Great. Interesting, Dan. Thank you very much.
Thanks, Lee.
Thanks.